The spinal cord is very much like a highway. Cars whizzing by so fast that you can barely make out their shape and color are very much like the electrical signals traveling through the spinal cord between the periphery of the body and the brain. But today we're not focusing on these signals. We're pressing the pause button and zooming in on the fine details of the highway itself. What kinds of cells and tissues make up and hold this road together? Let's find out now as we check out the histology of the spinal cord. So, what will we actually learn today? Well, we'll start with a general overview of the histological slide of the spinal cord. We'll then move on to learn about the meninges of the spinal cord and its sulci and fissures. Next, we'll look at neurons and their structure, followed by the two divisions of the spinal cord, gray and white matter, and their microscopic composition. And we'll, of course, finish up with some clinical notes. Now that we know what we will be learning today, let's start by taking a general look at the histological slide that will feature throughout our tutorial. The stain used in our image here is known as azon trichrome. With this stain, the nuclei appear red or orange, perhaps more maroon on our slide here. The connective tissue stains blue, and red blood cells stain bright orange. You can see a few in the lower left portion of the slide. The posterior aspect of the spinal cord is towards the bottom of the image here, and the anterior aspect is towards the top. The section we are looking at is from the thoracic region. But there is no point in me just telling you that. Let's just figure out what features you should look out for to be able to identify it for yourself. The first thing to note is the amount of white matter present in our section. As we move from inferior to superior along the spinal cord, the amount of white matter increases as more and more sensory nerve fibers join the ascending tracts to the brain. Therefore, we know that looking at our histological section that this is not taken from a lower lumbar or sacral region. Furthermore, the relative amount of gray matter is significantly higher in cervical and lumbosacral regions, as motor neurons supply a large number of structures in the limbs originating here. The thoracic and upper lumbar regions have relatively small amounts of gray matter by comparison. There is another small clue that tells us that this is the thoracic spinal cord, but I'll share that with you later on this tutorial. Now onto the main event. Let's take a closer look at the histology of the spinal cord, starting with its covering layers known as the meninges. First, we have the outermost meningeal covering known as the dura mater. It gets its name from the Latin for tough mother, which makes sense considering it is a tough, thick layer of dense connective tissue that forms a protective cover for the spinal cord. You can see it in this slide, but the dura mater covers the spinal roots as well as the spinal cord itself. It is continuous with the dura mater of the brain, as are the other meningeal coverings. The dura mater itself is composed of an outermost loosely arranged fibroelastic layer, a middle fibrous portion, and an innermost dural border cell layer. As this layer contains no extracellular collagen, it does not stain blue like the outer layers of the dura. And the next layer is the arachnoid mater. It is a loose connective tissue layer which is in close contact with the dura mater and sends tiny trabeculae to the innermost layer, the pia mater. The outermost part of the arachnoid mater is formed by a thin layer of squamous arachnoid cells which form a barrier layer. It is named after the spiderweb-like appearance of its trabeculae from the Greek arachne for spider or cobweb. This cobweb structure is so fine that it is normally lost in routine histological preparations. Much of the vascular network supplying the spinal cord is embedded in the arachnoid mater before it enters the tissue. The pia mater is the most delicate layer of the meninges covering the spinal cord. Its name is derived from the Latin tender mother, and just like the arachnoid mater, it is formed by a thin layer of simple squamous epithelium of pial cells. You've probably already noticed that there is occasionally a small gap between the arachnoid and pia mater. This gap is known as the subarachnoid space, and in a living individual is filled with cerebrospinal fluid. It is actually the pressure of the fluid which pushes the arachnoid mater so closely to the dura mater. Of course, it will come as no surprise that this fluid is missing in our section, and therefore the space will often have collapsed in much of the histological section. So, the main arterial supply of the spinal cord is delivered via 3 main longitudinal arteries, the anterior-most of which is embedded here in the arachnoid mater. The large vessel which you can see now highlighted is the anterior spinal artery, which arises from branches of the vertebral arteries and descends down the length of the anterior spinal cord. Surrounding it are a number of its branches. Of course, most arteries have a venous counterpart, and here we can see the anterior spinal vein, which we can easily identify due to its flattened lumen and absence of a defined muscular coat like that seen in the anterior spinal artery. The blood supply of the anterior spinal cord is reinforced by numerous anterior radicular arteries, which you can see here beside this spinal nerve anterior root. In the case of the thoracic spinal cord, these radicular arteries arise from the posterior intercostal arteries. The blood supply of the posterior spinal cord is supplied by the other 2 longitudinal arteries of the spinal cord, which are the posterior spinal arteries. These are usually of a small caliber than the anterior spinal artery and are therefore sometimes a little harder to identify. They usually arise from the vertebral artery or posterior inferior cerebellar arteries and run the entire posterolateral aspect of the spinal cord. And once again, you should be able to find a posterior spinal vein or 2 in the arachnoid mater. Let's begin to turn our attention to the spinal cord itself now, beginning first with this septum-like structure seen here. And this is known as the anterior median fissure, and which is lined by an investing folded layer of the pia mater. Looking at a histological transverse section, you can see how deeply the fissure penetrates into the spinal cord. Whereas if you were looking at its external surface, the anterior median fissure would appear merely as a shallow groove. Right opposite to the anterior median fissure, you'll find the posterior median sulcus, which is a shallow groove on the posterior aspect of the spinal cord. From it, a posterior median septum extends towards the central canal. As you can see, the posterior median septum is much less defined compared to the anterior fissure. The anterior median fissure and posterior median sulcus and septum divide the spinal cord into 2 symmetrical halves. Now it's time to dive into the microanatomy of the spinal cord, starting with the gray matter. In our cross-section, there are 2 clearly identifiable areas, gray matter and white matter. Let's start with our innermost of them, the gray matter. You may have noticed that it does not appear gray in this section. This is because it has been stained to highlight various histological structures found within it. The gray matter consists mostly of cell bodies of neurons and glial cells, which provide support and protection for them. The gray matter is generally butterfly-shaped and can be divided into 3 regions in the thoracic region. The rounded larger projections are known as the anterior horns or columns. The nerve cells found in the anterior horns are motor neurons. Opposite to it, we find the posterior horns or columns. They are occupied by interneurons, which make connections within the spinal cord, as well as neurons of the ascending sensory pathways. Between the anterior and posterior horns of the spinal cord is a region appropriately known as the intermediate zone, which largely contains neurons with properties similar to those found in both the anterior and posterior horns of the spinal cord. At the lateralmost aspect of the spinal cord is a small projection of gray matter, which is known as the lateral horn. This contains cell bodies of preganglionic sympathetic neurons that communicate with the sympathetic trunk via the anterior roots of the spinal cord and white rami communicantes. This tiny region is only present in the thoracic and upper lumbar spinal cord, which is our final clue to help us identify this section as the thoracic spinal cord. Before we move on to the cellular composition of gray matter, there are a couple of structures I would like to quickly mention. First up is the central canal. It is a channel which extends the length of the spinal cord, and in a living individual is filled with cerebrospinal fluid. The central canal is continuous with the ventricular system of the brain and is lined with columnar or cuboidal cells known as ependymal cells. Anterior to the central canal is the anterior gray commissure. It is a narrow band of gray matter which allows communication between the anterior 2 sides of the gray matter of the spinal cord. Similarly, we have the posterior gray commissure, which is located posterior to the central canal. Now let's take a closer look at the composition of gray matter. We are looking at the anterior horn at higher magnification. So the most obvious cells which we can identify here are these large, darker staining ones here, which are cell bodies of motor neurons. They're about 10 times the size of the surrounding glial cells, but only compose about 1 in 10 of the cells found here. If we look at this neuron here, we can get a better appreciation of a multipolar neuron. Extending from the cell body are dendrites and an axon. Sometimes it's not so easy to tell a dendrite apart from an axon. However, there are a few telltale clues which can help us figure out which is which. Dendrites, as you would expect, are generally thinner and shorter, and axons are somewhat larger. However, it's not always very obvious. Something that you might notice, however, is that there is sometimes an abrupt change in color between the cell body and a projection coming from it. And this process is a lot lighter than the cell body. That is because the cytoplasm in the cell body and dendrites contain structures known as Nissl bodies. These have a high ribosome content and are associated with protein synthesis in neuron cell bodies. And as they are absent in axons, they appear lighter in color. So if a cell process suddenly becomes lighter, you know that it is likely to be an axon. And with that, we have covered the main points about the neurons of the spinal cord, but there's still plenty of unknown structures surrounding them. Contrary to how it may seem from the way people talk about the composition of the spinal cord, neurons are not the most abundant cells in the spinal cord. In fact, they are outnumbered roughly 10 to 1 by cells known as neuroglial cells, or simply glia, which you can see dotted all over the place. Glial cells of the central nervous system, which consists of the brain and the spinal cord, are known as central neuroglia and carry out various supportive functions. There are 4 types of neuroglia: astrocytes, oligodendrocytes, microglia, and ependymal cells. Astrocytes are the most abundant and the most diverse of the central neuroglia. They provide the physical and metabolic support to neurons. They have a large number of processes and get their name from their star-like appearance. However, in routine histological section, these processes are impossible to make out and only cell bodies are visible. Their function is very variable. Astrocytes regulate ion concentrations around neurons. They contribute to the blood-brain barrier, regulate vasodilation in the central nervous system, as well as moving substances between neurons and capillaries. Astrocytes are about 10 times smaller than the neuron cell bodies, and the whole cell is about the size of a neuron nucleus. You'll recognize these cells by their small, often elongated or ovoid, dark staining nuclei. They also contain very little cytoplasm. The second type of glial cells we're looking at today are oligodendrocytes. You may know that their primary function is to produce myelin sheaths for axons. They are the central nervous system equivalents to Schwann cells. Similarly to astrocytes, they have processes, but in an oligodendrocyte, these are less numerous. However, in our gray matter, oligodendrocytes are not associated with myelin sheath and are known here as perineuronal satellite oligodendrocytes or simply non-myelinating oligodendrocytes. These are characterized by their small, dark staining round nuclei surrounded by a halo which gives the cell a fried egg appearance. This halo is an artifact of tissue processing and, like I said, has nothing to do with the myelin sheath. The function of oligodendrocytes in gray matter is actually not yet defined, but it is suspected that it may play a role in repairing neuronal injury. The name microglia speaks for itself. These cells are the smallest of the glial cells. If astrocytes were the size of a neuron nucleus, these little guys are roughly the size of a neuron nucleolus. These cells are roughly as common as neurons in the central nervous system and are distributed evenly in the gray and white matter. Microglia are phagocytes, so they engulf damaged cells and invading microorganisms. In a routine preparation, microglia can be identified by their tiny, elongated nuclei in contrast with the larger, round nuclei of other glial cells. We have pointed out one of these cells, which could be microglia, but in reality, these cells can be very difficult to identify. Our last type of glial cells are the ependymal cells, which are cuboidal in this instance, but can also be columnar. These cells line the cerebrospinal fluid-filled spaces in the central nervous system, in this instance, the central canal. These cells may sound like epithelium, but they're not. The main difference is the lack of basal lamina. Ependymal cells are connected by tight junctions at their apical ends, which stop cerebrospinal fluid from seeping into the intercellular space. You'll often find cilia or microvilli at their apical surfaces, which are adaptations for transporting fluid. We have covered the structures of gray matter, so now we're going to tackle the microstructure of white matter. The white matter is so known because in dissection it appears light due to the myelinated axons that populate it. There are three areas which the white matter is divided into. The first of which, the anterior funiculus. It is limited medially by the anterior median fissure and extends to the most lateral of the anterior nerve rootlets. The lateral part of the white matter is occupied by, surprise, surprise, the lateral funiculus. It is limited by the anterior and posterior nerve roots. Finally, we have the posterior funiculus, which is, of course, the posterior division of the white matter. You might have already worked out that it is limited by the posterior nerve roots and the posterior median sulcus. Just like the other two divisions, this is a paired bilateral region. It's important to note that white matter is also divided into white matter tracts. However, this cannot be readily identified in routine sections as the grouping is based on function rather than structure, so that's a tutorial for another day. The two halves of white matter communicate through a structure known as anterior white commissure. It is a thin band of white matter that lies anterior to the central canal, located between the anterior median fissure and the anterior gray matter. Now let's have a look at the microscopic structures of white matter. First up, you'll notice that compared to gray matter, the white matter has a sort of grainy appearance. That's because it is full of myelinated axons running up and down the spinal cord, which have been cut transversely. The small dark spot in the middle is the cross-section of an actual axon. It is surrounded by a clear area which is known as a myelin space, which is created after the myelin is washed out during preparation of the section. Scattered around the white matter once again are glial cells. The most abundant glial cells in the white matter are myelinating oligodendrocytes, which makes sense as they produce the myelin surrounding the axons. They feature a small round dark staining nucleus, and this is probably an oligodendrocyte here. Of course, we also get other glial cells in the white matter, such as astrocytes, which have relatively a large oval and less dense staining nuclei compared to that of an oligodendrocyte. Microglia are also present, but are very difficult to find and are more likely to be confused with unmyelinated axons. The axons of the white matter just don't travel up and down the spinal cord, they also exit the spinal cord via rootlets, which contribute to spinal nerves to reach the periphery of the body. And here you can see a rootlet of an anterior root, which looks quite similar to the white matter, but is separated from it by a meningeal covering. That concludes the histology part of this tutorial, but don't run away yet, because we've still got to discuss its clinical significance. Astrocytoma is a type of glioma, which is a cancer of the supporting glial cells. As the name suggests, astrocytoma affects astrocytes. It can affect both the brain and the spinal cord. When in the spinal cord, it manifests as weakness and disability in the area that is innervated by the region of the spinal cord affected by the tumor. It is diagnosed using a neurological examination, including checking the patient's balance, strength, reflexes, and coordination. A suspected astrocytoma can be confirmed using medical imaging. Normally this is an MRI scan, although sometimes a CT or PET scan can be used. Treatments, as you may expect, include excision of the tumor, chemotherapy, and radiotherapy. Prior or during the surgery, a biopsy sample may be obtained from the tumor, which is then used to determine its aggressiveness. Astrocytomas are assigned a grade from 1 to 4, 1 being the least aggressive. And we're done jamming your brain full of new information, but before we finish up, let's summarize what we learned today. We started by familiarizing ourselves with our histological slide, looking at the features of the spinal cord cross-section at the thoracic level. We saw that gray matter occupied a small part of the cord in proportion to white matter, and the cross-section had an overall round shape, compared to the flattened shape of some other regions. We also saw the lateral horn, which is found only in the thoracic and upper lumbar regions. Next, we tackled the layers covering the spinal cord known as the meninges. We saw that the dura mater was made of dense connective tissue and had a protective function. The middle layer, the arachnoid mater, consisted of loose connective tissue which formed trabeculae, giving it a cobweb-like appearance. The thin inner layer, known as the pia mater, consisted of connective tissue and a single layer of squamous epithelium. It's adhered tightly to the spinal cord. Between the pia and arachnoid mater, we saw the subarachnoid space, which holds cerebrospinal fluid in a living individual. We saw that the pia mater penetrated the white matter at the spinal cord and created an anterior median fissure, and the posterior median sulcus, as well as the posterior median septum. We then dove straight into the gray matter of the spinal cord. Here we identified its three main divisions: anterior, posterior, and lateral horns. We saw that the two sides of the gray matter communicated through a central region known as the gray commissure, which was also the location of the central canal. This is where things got really interesting because we started looking at the composition of the gray matter and all the microscopic structures which form it. First up, we saw large neuron cell bodies scattered around. In some of them, we could identify a few processes, which allow us to determine that the neurons we were looking at were multipolar. We also had a quick run through the structure of a typical neuron. We started with the cell body, which contained a nucleus, nucleolus, and Nissl bodies. Extending from the neuron cell body were information receiving dendrites and information transmitting axons. Surrounding the neurons, we saw numerous support neuroglial cells. We identified 4 types: astrocytes, oligodendrocytes, microglia, and cuboidal ependymal cells. Astrocytes being the most abundant in gray matter, and ependymal cells being only present in the central canal. We then jumped over to look at white matter. We identified 3 areas here: anterior, lateral, and posterior funiculi. We found that the 2 halves of the white matter are connected via the anterior white commissure found anterior to the central canal. In the white matter, we predominantly found myelinated axons and oligodendrocytes responsible for myelination. Here we also saw the anterior rootlets, which contribute to the formation of the anterior spinal root. And finally, we talked about astrocytoma, a cancer arising in astrocytes, for our clinical notes section. And that is it. We hope you enjoyed this tutorial. I hope to see you next time.